What connects the probability field of an electron orbital, the vibrations of a guitar string, and the data curve of an audio signal? They all map to the exact same geometric space. To see how, we need to establish our baseline. We start with inner product spaces, spaces equipped with a dot product, denoted here by x and y in angle brackets. When these spaces are complete, meaning they don't have any missing limit points, we call them Hilbert spaces. Within these spaces, we look for orthonormal sets, vectors that are perfectly perpendicular to each other and scaled to a length of 1. Once we have an orthonormal set, we can represent incredibly complex elements in our space by projecting them onto these basis vectors and adding them up as an infinite series. You have likely seen this process with sines and cosines in a standard Fourier series. But sines and cosines are not the only tools available. We can swap out those trigonometric functions and build our bases entirely out of polynomials. Using polynomials as an orthonormal basis gives us a highly effective toolkit for approximating continuous functions and solving boundary value differential equations. This chart shows the standard sequence of polynomials, 1, t, t squared, and t cubed, plotted on the interval from -1 to 1. They are linearly independent, but they are completely entangled. They are not orthogonal. If they were truly orthogonal, calculating the area under the product of any two curves would give us exactly 0. As the graph shows, the resulting area is distinctly non-zero. To fix this, we apply the Gram-Schmidt process. We take the original sequence and systematically subtract out the overlapping projections. This process spawns an entirely new family of polynomials that are perfectly orthogonal to one another across our specific interval. Gram-Schmidt acts as our mathematical engine here. Instead of forcing us to guess solutions to complex differential equations, it mechanically generates the exact polynomial families we need. This graph shows the first 3 orthogonal polynomials generated on that finite interval from -1 to 1. These are the Legendre polynomials, denoted P0, P1, and P2. Deriving these manually with Gram-Schmidt gets tedious quickly. We bypass that entirely using Rodriguez formula, a shortcut that lets us compute the nth Legendre polynomial directly through repeated differentiation. The proof that these are orthogonal relies on that specific derivative structure. When you take the inner product and use integration by parts, Rodriguez formula forces the lower degree boundary terms to evaluate to 0, cleanly annihilating them. The resulting polynomials happen to be the exact solutions to the Legendre differential equation, which appears frequently in potential theory. When a physical problem, like calculating the electric potential inside a sphere, is naturally bounded within a finite interval, Legendre polynomials provide the precise geometric basis required to construct the solution. If we expand our interval to span from -infinity to +infinity, we break our previous model. Standard polynomials like t squared grow without bound, meaning any attempt to calculate their inner product yields an infinite area. We have to control that growth. We solve this by redefining our inner product, so the polynomials are multiplied by a wake function, specifically e to the -t squared over 2. This exponential decay overpowers the polynomial, pinning the tails firmly to the horizontal axis, so the total area remains finite. By applying Gram-Schmidt with this new weighted inner product, we generate the Hermite polynomials. The true orthonormal basis functions here are the polynomials physically bound by that exponential weight function. This exact mathematical structure allows us to solve the time-independent Schrödinger equation for the quantum harmonic oscillator, determining the allowed energy levels. These weight functions represent strict physical boundaries, like the restoring force acting on a particle, that keep an infinite system mathematically sound. Now, what if our physical domain starts at 0 and extends to +infinity? Think about what kind of weight function we need to prevent divergence on this half-infinite interval. We only need to suppress growth in the positive direction. A standard exponential decay, e to the -t, perfectly bounds this specific interval. When we orthogonalize with respect to this new weight function, we generate the Laguerre polynomials. In physics, this half-open interval typically represents the radial distance outward from a central point. Consequently, Laguerre polynomials are what we use to solve the radial component of the Schrödinger equation for the hydrogen atom. The physical boundaries of your domain directly determine your weight function. That weight function dictates precisely which family of orthogonal polynomials you must use to build your solution. If you are solving these problems, keep 2 rules in mind. First, standard polynomials and orthogonal polynomials are distinct tools. Do not swap them blindly. Second, if your integration limits go to infinity, you must include the appropriate weight function to keep your inner product finite. To summarize, for the finite interval from -1 to 1, use Legendre polynomials. For the infinite interval, use Hermite polynomials with a Gaussian weight. And for the half-infinite interval starting at 0, use Laguerre polynomials with a standard exponential weight. If this breakdown helped you clarify functional analysis, hit the like button and subscribe. Let me know in the comments which theorem or textbook chapter you want us to visualize next. Orthogonal polynomials take the abstract geometric structures of Hilbert space and convert them into the concrete functions we use to describe the physical universe.